Okay, we'll get started here. Any questions? Questions? The class is really slimmed down because the drop deadline was last week on Friday. So if your partner dropped the class, we'll have to regroup for the formal report.
We already started.
You already started? Okay, good. All right. We're going to continue on. We're going to finish up chapter 9 today. Well, get through most of it. We might not finish all of it. But before I do chapter 9, I need to tidy up some loose ends from chapter 7. And so let's talk about that first before. And one of the loose ends, this is something that was asked earlier of me, and that is, is Petrucci wrong to say that the higher or the more positive the number, the higher the energy? No, for certain things that's true. For example, when we look at the hydrogen atom, if you look at the H atom, the lowest energy for the electron in the H atom is minus 2.17 times 10 to the minus 18 joules. That's the lowest energy. What's the highest energy possible? Zero. And so this would be the n equals infinity, and this is n equals 1 here. So we have the 1s, and then we have, infinity squared orbitals up here. But anyway, going back down to this, here, the higher the number, the higher the energy. So if we were to compare, let's say, minus 2.17 times 10 to the minus 18 joules versus 0 joules, which one's higher in energy? 0 joules. Okay, but when we're thinking about delta H and delta U, it's a different thing. Delta H and delta U is a change in energy. A change in energy like that, you're going to think a bigger positive delta H or delta U just means we have to climb a higher mountain, or a bigger negative delta H just means we have a lot longer drop, over the waterfall. And so that's one of the tricky things that you have to remember, and they just expect you to remember this. But there's another thing that's tricky that they expect you to remember, and that is Appendix D. So let's talk about Appendix D. And let's take a look at some numbers in Appendix D here. Let's adjust this. All right, the first data, we don't want D1, so let's fast forward here. This data table. All right, we're just focusing on the first column, delta H formation. This other stuff's covered in Chem 1B. But you look at the delta H formation for aluminum, what is it? Zero. You expect it to be 0. Why? Right. Actually, we're forming 1 mole of aluminum solid at 298 Kelvin from what? 1 mole of aluminum solid at 298 Kelvin. So if you're going from 1 mole of aluminum to 1 mole of aluminum, everything else being the same, is there any change in energy? No. And so we expect that to be 0. That's kind of like that's definitely an absolute 0, right? There shouldn't be any energy change there. And so let's take a look at some of these other energies. Minus 531. Actually, here's the biggest one. Minus 3441. And so we see minus 3441 kilojoules per mole. What's the story behind this number here? Minus 3441. What is that for? You have a pretty big drop in energy. What's that? That's the heat released from what? From the reaction. What is the reaction? Yeah, so let's write it's a big drop, and so we know we're going to see a big drop in energy. Actually, this one. We must be pretty high, and then we must be going pretty low. Delta H here is minus 3441 kilojoules per mole. All right, what is this drop for? Is it for Al3 plus sulfate yields AlSO4? Is that it? Or is it for, what's the reaction here? Aluminum plus sulfate. Is that right? Aluminum 3 plus sulfate, and then we balance it to get Al2SO4 3.
No.
Is that right? We're forming, this is it, we're forming 1 mole of solid aluminum sulfate from what exactly?
Alumina, oxygen, and the
Yes, we have 2 aluminums plus, how many sulfurs? 3 sulfurs plus 12 oxygens. And so is that right?
No, not the oxygen.
Yeah, actually the oxygen's wrong.
6 oxygen.
It should be 6O2. And we need the state. So what is the state for aluminum?
Solid.
Solid, sulfur,
Solid.
and O2?
Gas.
Yes, those are the stable states under ambient conditions. And so there's a tremendous amount of energy released. What this tells me is that aluminum sulfate is quite a bit more stable than a mixture of aluminum, sulfur, and oxygen. And so when we're thinking about that, yeah, there's going to be a lot of heat release. Actually, the amount of heat released in this is going to be minus 3441 kilojoules, right? And so, what exactly is delta H? Is delta H always the amount of heat? Because is delta H defined as the amount of heat that's released?
The change in the heat.
The change in the heat? We mean this was hot, extremely hot, and this is extremely cold? What is H and what is delta H exactly? Because H, we started off at H initial, we end up at H final. And so what exactly is H? Is H the heat? Is the energy? Okay, if it's the energy, how does H differ from U, let's say? How does H and U differ? Okay. You're right. It is U plus PV. That's correct. And so what would you call enthalpy then? What is the enthalpy exactly?
Sum of the internal energy and product.
Well, U is it only potential energy? No, U is
Kinetic.
potential plus
Kinetic.
energy. And so these kinds of things, what you want to do in this particular course is you want to at least come up with some kind of definition where it's fairly clear in your mind what H is and what delta H is and that type of stuff. Because as I was telling the morning class, when you continue on, let's say you're going to transfer, go to let's say UC, they aren't going to wait. They aren't going to wait for you to get the definitions. They're just going to assume you know the definitions very well and then just move on. And while they pile on a whole bunch of additional stuff. And so in this case, we just finished the exam here, and so we should know what H is. And I have different ways of thinking about this myself. One of the things that I call delta H is what did I call that? I called that the net energy after you deduct the total energy for any kind of taxes or bonuses, or maybe there's no tax or bonus, and the total energy is what you're going to get. Does that make sense? Or, you think of some other way that you can remember it. But basically what delta H is delta H is the energy, the total energy change, compensating for the fact that we might have a
Sure.
compensating for the fact that we might have a tax, bonus, or nothing. In other words, when I think about enthalpy, the enthalpy change is the change in total energy, keeping track of the PV state. The PV is an energy state, and this tells us how the system is going to interact with the surroundings. Is it going to get taxed? Is it going to get a bonus from the surroundings? We need to understand the PV state in order to deal with that. But is delta H always going to be heat? No, we saw that it doesn't have to be. When you burn methane in a vehicle, let's say one of those compressed natural gas vehicles, CNG vehicles, when you burn methane in a vehicle, does it convert all the energy into heat, and then you use that heat maybe to boil some water, convert it into steam, and then there's a steam turbine in the middle of the car, is there? No. In fact, what we're doing is instead of doing this, we're just adding more work terms here, and we're converting that potential energy change into work, straight into work. We aren't going potential energy change to heat to work. And so because of that, the way I think about delta H is I think of this as the net energy. Now you can use that net energy to do whatever you want. You could try to convert it all to work, right? That's fine. It doesn't have to stay as heat. Does that make sense? Somewhat? Well, these are the things you want to think about, as you're going along. Because thermodynamics is such an important course, for engineering, for biology. Even my kinesiology roommates, when I was at UCLA, they had a kinesiology major there, and I didn't know what kinesiology was, but they were doing one of these problems. They were trying to calculate the energy required for jumping. Have you heard? Running and jumping. So that was a kind of interesting calculation. But those are, where do they get that energy? They're going to get that energy from foods, right? Well, anyway, so a little bit of review here. Now, this is the way I think about it. Well, that's a lot of energy that's released when we form 1 mole of aluminum sulfate from the elements, right? In other words, aluminum sulfate must be quite stable. And so when we have a table like this, we like to look, what's the biggest positive value? What's the biggest negative value? And what does the 0 mean? And so what the 0 means here. Well, this table, we look at it, we can go through the values. Here's a positive value, 35.6, another positive value. It looks like most of the values are negative. That is, the compounds are favored over the elements. And that's the case. When you go out to the desert, and you look for deposits, you usually don't find like magnesium deposits. You find, magnesium sulfate deposits. And so most of the elements that are found exist as compounds in nature, except for some that are much more stable as the element. That would be like gold, right? Mm-hmm. Gold you would find in nature is the element gold, not necessarily the compound. And so let's take a look at some of these, and you can see, do you see most of them are negative? Mm-hmm. Except here, here's one that's fairly positive, but take a look at what it's for. This is 111.9, what is it for? Atomic bromine. Does bromine like to be as atoms or diatomic? Diatomic molecules, so that's not going to be favorable there. And so far plus 111, here's plus 716. Plus 716, that's a pretty big positive number. But look what it's for. Gaseous carbon atoms. Unstable. So we know that's going to be unstable. C2N2, okay, there's a compound that seems less stable. CS2, less stable than the elements. Uh-huh.
So do negative numbers mean more stable that way, and positive numbers mean unstable that way?
Yes. Right. But relative to what? You know, relative to what? Negative number means something, positive number means something. And so we're comparing it to zero. Right. And so this is when I look at a table like this, I'm thinking more like Celsius, you know, or I don't know, there's a zero here, so we have negative numbers. This means more stable than zero. Well, negative Celsius just means colder than zero. You know? And positive numbers should be greater than zero. And so I just scan the numbers like this, get some kind of general feeling for the numbers. We do. This is, you know, what's not often done. Well, a lot of people, when they get a table like this, they don't do anything. They always figure, well, I can go back and look at the table. Okay. All right, so let's go back and now let's take a look at some more numbers here. So I look at this and then go, okay, I have solid aluminum here, and that's 0. And then I go to Al3+. If I look at Al3+, it's minus 531, which tells me what? Al3+ seems to be quite a bit more stable than aluminum. So aluminum going to Al3+ looks to be quite favorable, right? Unfortunately, somebody should have stopped me there. Somebody should have stopped me there because that's wrong. I mean, my thinking is totally wrong. My thinking is totally wrong because I just did a serious violation here, and there should be some kind of thermodynamics judge that tells me, stop, you just violated something. You know, but there is no thermodynamics judge, and you have to self-police yourself. There's nobody that's going to tap you on the shoulder and say, excuse me, but you just made a big mistake, right? Nobody except yourself. And so that's can you see why so many people end up failing thermodynamics? Is because there are actually 2 tables in here. You know, this doesn't quite work, and the way you can see that there are 2 tables in here is by going down. Once we scan this and we look carefully and we start reading the numbers, we're going to see something very odd. And so let me show you that. Here. So everything looks okay until we get here. When we get here, maybe this is a typo, you know, but you look at it, okay, one of these zeros is right, you know. One of these zeros, there's no problem with. The other zero, there seems to be something odd about it. And so which zero do you think is the odd one?
Hydrogen gas.
Hydrogen gas, H2 gas. This one? So it's formation of hydrogen gas, H2 gas, from what? From hydrogen gas. So we're forming hydrogen gas from hydrogen gas. Should there be any energy change? No. The odd one is this one, because we're forming H plus from what? Yeah, from hydrogen gas. And so if we go, actually we'll need 1/2 H2 gas goes to H plus AQ. This is delta H. Delta H of formation. It's formation of 1 mole of H plus from the elements in there. stable state. And it has this little superscript. What does that little superscript 0 mean? Okay, it means standard conditions, which are what? 1 bar for H2 gas. 25 Celsius? No. It's not 25. If this were at 25, which it is, we'd write it down here, 25 degrees Celsius, as an added constraint. The reason is there's no standard temperature thermodynamics. And so we could have standard conditions under different temperatures. So 1 bar for the gases and
Formation of 1 mole.
not and formation of 1 mole, but this little superscript means superscript doesn't mean 1 mole. This means 1 mole. This superscript means formation of, well, at 1 bar and or 1 ATM, it could be 1 ATM, and 1 molar solution. So the gas is going to be at 1 bar, 1 ATM, and the solution is going to be at 1 molar. That's what that means. What is the delta H for this? 0. That means, oh, they must be equally as stable. I mean, there's no energy change. What do you think? Is there no energy change to convert hydrogen gas into H plus? You know, take away the electron? In other words, what we have to do, you have a hydrogen molecule here. First thing is you got to break the bond. So now we have hydrogen atoms. We take one of those hydrogen atoms and then we got to come in there and pull the electron off. Pull the electron off and put it in water, 1 liter of water. No energy change at all?
Is it more so about the state that it's in? Like, as a gas?
Well, maybe after breaking the bond and taking the electron off, that costs us energy, doesn't it? I'd expect this to be endothermic because shouldn't it be becoming less stable? And then, but maybe we get some energy back when we put it in water. Maybe the water helps stabilize the hydrogen ion. Right? And so maybe it's completely break even. And so do you think this is exactly 0 or close to 0? So how many sig figs? 10? A lot?
4.
You know, maybe it's really 0.00001 or negative 0.00005, and they just rounded it to 0. Does that make sense? Would you round it? You know, Avogadro's number is so big. Would you just go ahead and round it to infinity? Would you round Avogadro's? It's so big, we might as well round it to infinity. Or how about the size of the atoms? The size of the atom's so big, small, I'm going to just round it all. I'm going to round all of them to 0. Does that make sense? No, that's why we have scientific notation. We don't have to round it. If it's 0.0013, then we'll just do scientific notation. 1.3 times 10 to the minus 25. We're not going to round it to 0, are we? And so, getting back to this is odd because I expect this not to be 0. I expect there to be some energy involved in breaking the bond, ionizing it, and putting it in water. And so it's odd. And the answer is, it is odd. This is odd because now we have 2 zeros in here. And so this table is very weird because this table has, well, you know, if I wrote the book, I would have separated the data into 2 separate tables. One table would be like the absolute temperature, like Kelvin. The other table would be like the Fahrenheit. And so an example would be like this. What's a higher temperature? 0 or minus 10? What's a higher temperature? 0 or minus 10? Okay, so 0 Kelvin is a higher temperature than minus 10 Fahrenheit? 0 Kelvin is higher temperature than minus 10 Fahrenheit? No, so you got it wrong, right? But was there a temperature judge saying, okay, wait, you got it wrong? No, there's nobody saying you got it wrong. Well, the problem is unfortunately there are two scales in here. There's a Fahrenheit and there's a Kelvin. Now, if you look at this zero is absolute. We know this is a real zero because there should be no energy change here. The second zero is not. The second zero is what we call a arbitrary zero. For example, 0 Fahrenheit. Is 0 Fahrenheit something? I mean, what's that reference to, or is that totally arbitrary? You know, what did Fahrenheit choose as 0? Was there some specific phenomena or some specific... No, I think it's totally arbitrary. There was a very cold day and he called that 0, I think, right? But I'm not sure. And so that's the same thing here. This is not really 0. This is some kind of arbitrary. And so what we have here is we have two different scales and we can't compare the two. And so I asked you the question earlier. I asked you this question. Aluminum solid is 0. Al3 plus Aq is minus 531. Which one's more stable? How do you know? You know, how do you know? Because did I tell you the relationship between the two scales? Like, for example, how do you know minus 213 Fahrenheit versus 63 Kelvin? You know, which one is colder? Well, you can kind of figure it out in your head because you know, oh, the relationship between Fahrenheit and Kelvin, but this one, do you know the relationship? Not off the top of your head, right? And so this, you cannot compare these two numbers. You cannot compare these two numbers because this is the exact same question. Which is a hotter temperature, 0 or minus 10? This is asking you the same thing. Which one's bigger, 0 or minus 531? Well, how do you know? Because these are two different scales with two different 0 reference points. And so we have a problem here, and the problem is this, but they expect you to know this. They expect you to know that you cannot compare ions which are referenced differently than elements and compounds. So for example, I can compare aluminum with aluminum sulfate, no problem. Here, you know, as far as the numbers go. But here I cannot compare aluminum with aluminum 3 plus directly because these numbers mean different things. This number is based on a Fahrenheit scale. This number is based on a Kelvin scale. How can you compare the two in terms of magnitude? And so in other words, this is why I want to separate into two separate scales. I put all the ions into one table and all the elements and compounds into another table and tell you not to compare the two numbers directly. Because even though they look the same, you know, one is for apples, the other is for oranges, you know, and so here if I'm asking you which one's the biggest apple and you tell me minus 531 is the biggest orange, does that make any sense? No, and so you got to be careful with this table. Now, this table is even more complicated. Oops. This table is even more complicated because it's not just two tables in one, it's actually 3 tables in one. And so why did they decide to give you so much extra work? You know, why not just keep it simple and just have the same reference for everything? And so let's talk about the reason why they did this. And so what we're going to do is we're going to look at delta H of formation for HCl. Delta H of formation for HCl is minus 167.2. If we look at this, then you'll see where the problem originates from. And so this is the same thing in your book. So what we can say about this is, okay, delta H minus 167.2. This is the formation of HCl AQ. from what?
1/2 shit.
1/2 H2 gas
CO2.
plus 1/2 Cl2 gas. Okay. Next, HCl is a strong electrolyte. And so HCl doesn't occur as intact molecules, but instead it will ionize or hydrolyze completely. When HCl ionizes, what does it ionize to? H plus and Cl minus. It being a strong electrolyte, these ions are going to be independent of one another. They aren't attached. And so the question comes here. How much of this 167.2 kilojoules is due to the formation of H plus, and how much is due to the formation of chloride? You know, is it 50-50, half of it? No. Is it 20-80, 10-90?
Can we get rid of that chart?
We can't go over this chart and calculate. No. This chart comes from these numbers here. Do you know where this chart comes from? A lot of these numbers come from? Experiment. You know, it's not so easy just to go ahead and theoretically calculate these using what theory? It's a theory of chemistry. Quantum mechanics. It's not so easy to go back and calculate. And so a lot of this came from calorimetry experiments. And let me talk about that. Where you can find a lot of these are in the JANAP tables. Have you heard of the JANAP tables? Mm-hmm. NIST, JANAP thermochemical tables. JANAP 4th edition PDF file. So let's click on fluorine. You see that? It's a lot of data there. You see this C? What's that? C. C is the symbol for specific heat or heat capacity. They did a lot of calorimetry here. And so, you know, this is a lot of work, basically. And let's go through. No, it doesn't work. So who's interested in thermodynamics?
Sean.
Sean, yeah. So I was always curious about this, JANAP. What does JANAP stand for? And so who's interested in thermodynamics? The U.S. military is interested in thermodynamics. And JANAP stands for Joint Army, Navy, Air Force. And their science divisions did a lot of calculations, a lot of experiments. Why they thermodynamics is so important in so many different so many different fields. And so yeah, everybody uses these. And these are freely available. I don't know how much they're doing now, but you know, there's huge volumes. And in fact, I have one volume of JANAP tables in my office. And so it's not, we don't calculate it. For example, the reason we don't calculate it, why don't you think we just calculate it? You know, we've spent all this time in Chapter 8 talking about the theory underlying chemistry, which is quantum mechanics, right? And so shouldn't we just be able to calculate what percentage of this is due to the H plus and what percentage of this is due to the Cl minus? Sure we should be able to calculate that. And so you go ahead and do the calculation, but you come to the realization of what? No, it's not that there's no reference. It's that the calculation is so hard that you have to use approximations. You can't solve it exactly. And when you use those approximations, you introduce error into the calculation. And those errors sometimes are quite large. So large that the numbers you get are unreliable. Of course, the calculations are getting better. So maybe, you know, as things progress, calculations get better, approximation methods get better, they can come up with it. But, you know, so we run into the situation. You've seen this situation before, too. The situation is going to be like this. Okay, if we want the delta H for this reaction, the delta H of the reaction is going to equal the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. So the products we got to do the delta H formation of H plus. We have 1 mole of that. We got 1 mole of chloride, so we'll need the delta H formation for Cl minus. Okay, these are the products minus the reactants. The reactants in this case are all elements in their standard state, and so those are going to be 0. And so this is going to equal minus 167.2 kilojoules per mole of HCl formed. Now, looking at this here, we have 2 unknowns and 1 equation. And so what do we do when we have 2 unknowns and 1 equation? Sometimes we'll just solve it to an equation. Sometimes we'll assume, make an assumption, come up with some ballpark. You know, what would you come up with a ballpark for delta H plus? Sometimes this is if we don't have a second equation. Sometimes we'll do this. This is the third one. Sometimes we'll just say, oh, you know what? I'm just going to arbitrarily define one of these as 0. And that's exactly what they did. They arbitrarily defined H plus as 0 and said that the delta H of formation is going to be minus 167.2 kilojoules for chloride and 0 kilojoules for H plus. And then you go, is that accurate? That's going to be worse than a calculation, isn't it?
Yeah.
But the situation here is that can you ever form a cation without an anion? No. Can you have a bottle of just pure anions? No, it would be so unstable. And so since you have to always form a cation with an anion, the cation might be too high, the anion might be too low, but they're equal and opposite. And so when you add up the cation with the anion, the errors systematically cancel each other out. And so this is like calculating altitude. If you calculate the altitude, altitude change, let's say an airplane climbs, do you have to measure from the center of the Earth to get an accurate calculation? No, you can pick any arbitrary point and then measure it relative to that point, because the error, that is the distance from the center of the Earth, will cancel out. And so here, this is estimating it. And the same thing here. The error in calling one too high and the other too low will cancel each other out so that the product is accurate. And so this is way off, this is way off, but when you add them together, oh, it's right. Right? And so that means that there are actually 3 tables here in one. We can compare elements and compounds. We can compare cations with cations, and we can compare anions with anions. But we do not want to compare cations with anions or any other combination. And so this table is, even though it looks so straightforward, it's not. This table is a trap waiting to trap you, it's waiting to catch you unsuspectingly making a incorrect comparison. And so you have to be careful. Does that make sense?
You said compare cations with anions?
No, you cannot compare cations with anions. You can compare, because the 0 point is different. For cations, the 0 point is H plus. What's the 0 point for anions? Who knows? There isn't. There isn't a fixed 0 point. It's just some point called 0. This chloride is minus 167.2. See, so we have 3 different, and so this would be a combination. When we look at the numbers here, it's a combination of Fahrenheit, Celsius, and Kelvin all in the same table without units. Nobody bothered writing the units. Nobody bothered writing the units because, well, actually, for one, the units are all the same, kilojoules per mole. But nobody bothered writing it because you can figure it out, you know? If you're dealing with elements and compounds, we must be on the Kelvin, right? The Kelvin, if we're dealing with elements and compounds, then we have this absolute zero. Right? The absolute zero is formation of the elements from the elements. If we're dealing with cations, then the analogy would be Celsius. If we're dealing with cations, the analogy is Celsius because now we have an arbitrary zero. The arbitrary zero is H plus. Right? Somebody said, okay, H plus is a good thing to call zero. We're going to call it zero. And then reference everything. That means what? That means, you know, when I did the first comparison is wrong. Aluminum, yes, that's zero. But aluminum 3 plus is minus 531 relative to H plus. And then anions would be like the Fahrenheit scale because who knows what zero is? You know, it was just defined this way. Chloride is minus 167.2. Is there really something that has zero? Probably not. And so 3 scales in one, it's just that the same thing happens, you know, the same thing happens over and over because in thermodynamics, for example, delta H, can you have any work? Will that be the amount of heat with any type of work? No, you're restricted, right? The type of work has to be P delta V work. But what if you accidentally calculate the amount of heat and the work was electrical work? Is that going to be right? No, but nobody's going to stop you. You can go ahead and do that calculation and get the wrong answer. Nobody will stop you. And nobody's going to tell you it's wrong. Just like over here. You know, nobody's going to stop you and tell you, wait a minute, you know, you're not reading this table correctly. So lots of things to keep track of, you know, with thermodynamics, and it's always something, you can always learn something.
Dr. Schmidt, what is the alpha solid?
I'm sorry?
The Al2O3. What is alpha solid?
Oh, well, okay, alpha solid. Aluminum oxide, that's Al2O3, is also called alumina. And aluminum oxide has, you guys have heard of isomers? Isomers are the same formula, different structure. Well, this would be the equivalent of an isomer of aluminum oxide. There are different kinds of isomers for aluminum oxide, except we don't call them isomers. We call them phases because aluminum oxide occurs as what we call a crystal lattice. And so there are different crystalline lattices for aluminum oxide. Alpha is just the most common phase for this, but there are other phases. And so this would be like calling carbon alpha and carbon beta. Carbon alpha might be graphite, carbon beta might be diamond. And so it's just a way of labeling those. In our book, how do they deal with carbon? Because, you know, for elements, for compounds we call them phases. For elements we call them allotropes. And so there are 2 phases, actually more than 2, but there are 2 phases of carbon here. Since it's an element, we don't call them phases, we call them allotropes. 2 allotropes of carbon. And we don't call them isomers because isomers, we use that term for usually organic compounds. But here, diamond versus graphite, we just put it in parentheses here. The other phases for aluminum oxide aren't shown. You probably can go into the JANAP tables and find those if you're interested. All right, so that's a little bit, some one loose end I wanted to tie up for chapter 7. Let's go back to chapter 9 now. Where did I leave off? We were talking about sizes of atoms. Do atoms have rigid walls? No. And so measuring sizes, we just usually take an average. For example, here, we just measure what we call the bond distance and take that bond distance cut in half and get the radius of the atom. But sometimes the atoms, the nuclei are pulled closer. Sometimes they aren't pulled as close depending on how strong the bond is. The stronger the bond, it tends to pull the atoms close to each other. The weaker the bond, the farther. And this could be for the same element. And so the atomic radius does change over a range. And so what do? We take the average. I think I talked about averages. When we have an average, we want the standard deviation or the 95% confidence. An idea of how what that is. Okay, and then we saw some size trends here. I think I left off. As we go left to right, so we start at lithium and go to fluorine. On the periodic table, lithium to fluorine, what happens to the size? The size drops pretty dramatically, Goes about half the size, 150 to about 75. It's quite a bit smaller. Shrinks by 2 And so what was the cause of this? Did we talk about that? No time? We ran out of time? All right, let's talk about that. We see this pattern repeated here. If we go from sodium to chlorine, the size decreases, potassium to bromine. So let's take a look at the size chart here. See if we can find it. All right, so we start at lithium, it's 150 picometers radius, down to fluorine, 71. Half the size. Do you see the pattern repeating? Big to small, big to small. So as we go from left to right in the periodic table, the size of the atoms shrinks to about half the size. We're looking at the gold. All right, now we have to ask, why is that? Because, beryllium has more stuff than lithium. Lithium only has 3 protons, beryllium has 4 protons. Lithium only has 3 electrons, beryllium has 4 electrons. So beryllium has more stuff. So if beryllium has more protons, more electrons, more neutrons, shouldn't it be bigger? No. Why? Because the protons. The more protons we have, the stronger the electrical attraction is, and it pulls in the electrons. And so as we go across here, the number of protons increases, and the size decreases. But the funny thing is, we'll jump, when we go from lithium to sodium, we have a lot more protons. Lithium only has 3 protons, but sodium has 11 protons. And so with 11 protons versus 3 protons, shouldn't sodium be much smaller? No, sodium is actually bigger. Can you tell me why? Because even though it has more protons, it has another shell of electrons. So let's talk about this here. And we're going to use, I think I started talking about hydrogen. Did I talk about hydrogen and helium?
The Z effect is smaller because of the shielding. Is that what it was?
Yeah. The first strange thing is when we look at hydrogen here, hydrogen to helium, helium is smaller. And we said it's smaller because 2 protons versus 1 proton. 2 protons can pull in the electrons a lot closer. This is the greater electrical attraction. And so when we get to lithium, we are predicting that when lithium has 3 protons, 3 positive charges here, then the electron should be pulled in very tight to the nucleus. And that's the case for, how far did I get here? Did I draw this? It's true. When I look at the, when I look at the 1s orbital here, actually I should try to draw more dramatic. Let me try that again. When I compare the 1s orbital here with lithium, the 1s orbital on lithium is a lot smaller. And so it does pull in the 1s electrons quite tightly. Okay, but the third electron is not in the 1s orbital. The third electron is in the 2s orbital. But that's okay. The third electron's in 2s, so the 2s gets pulled in very tightly, but it doesn't. The 2s does not get pulled in very tightly. And so the size is actually bigger than both hydrogen and helium. And so you got to think, well, with 3 protons in the nucleus, why isn't that 2s electron being pulled in more tightly? There are 3 protons there. And the reason is, did you guys write this down? The reason is because of shielding. Inner shell electrons are effective shielders. And so the net effect here is, as we go down the periodic table, we have increasing N, which means increasing number of shells with Z effective fairly constant. Okay, what was Z effective here? About, well, Z effective is the same as Z. Z effective is 1. Okay, what's Z effective here? How much of the nuclear charge will that see? About 1. Because of the shielding, when we look at a family, Z effective doesn't really change much. And so when we go, this is, hydrogen has a Z effective of about 1, lithium has a Z effective of about 1, sodium has a Z effective of about 1. The reason sodium has a Z effective of about 1 is because of this. Actually, it's hard to see the periodic table there, sorry. Do this again. Okay, how many electrons does sodium have? 11. Out of those 11 electrons, how many of those are core electrons or inner shell? 10. How many protons is 11? So you have 11 protons and 10 inner shell electrons. Those 10 inner shell electrons are effective shielders, which means they block 10 of the protons, leaving 1 proton. And so in other words, Z effective for sodium is about +1. But now, rather than filling the N equals 2 shell, we have the N equals 3 shell, so it's a lot bigger. And so as we go down the family here, we're just adding more shells, and therefore it's getting bigger. as we go across a period here, what we have is a little different story because, yes, we are adding one proton, but we are also adding one electron. And so if we add one proton and one electron, shouldn't the extra electron shield the extra proton and we're back to even? No, it doesn't because same shell electrons are not effective shielders. And so the size trend is this. The radius increases going down. The radius decreases going across. The radius decreases going across because Z effective increases. N is constant. Z effective increases because same shell electrons are not effective shielders. Same shell electrons not effective shielders. All right, same shell. Let me put shell in quotation marks because we know, this is the second shell here, right? This is the third shell. This is the fourth shell. Yeah. And so I put shell in quotation marks, and let me put a little asterisk here because of the transition block, of the transition metals. Take a look at the size of the transition metals. Starting with, let's start with vanadium. 132, 125, 124, 124, 125, 125. Look at it. 125, 124, 124, 125, 125. What's happening? There. The size is constant. And so each time I'm adding one proton, and I'm adding a same shell electron. But the size isn't shrinking like it should. And so there's a trick to this. The trick is, yes, this is the fourth shell, but I have to look at it a little bit more, in a little bit more detail. I have to look at it in more detail because these electrons I'm adding here are not actually going in the n equals 4. They're actually going into the n equals 3. And so what we're doing is each time we add a proton, we're also adding an inner shell electron. And so for the D blocks, we consider those inner shell. So the transition block, when we're thinking about this here, the size is not going to change much because we add a proton, we also add an inner shell electron, which effectively cancels out that extra positive charge and means that we're just back to even. And so the size flattens here. And we can see that in our earlier chart.
So n is going to 3.
Oh yeah. Here, this is the fourth shell, right? And so here we add a proton, boom. We also add an electron, boom. The electron's going into the 4s orbital. Now we add a proton, boom. We also add an electron, but the electron is going into the 3d. Now the 3d, since it's inner shell, is going to be more effective at shielding a 4. If both electrons went into the fourth, let's say the fourth level here, then it's ineffective. But if one electron is actually one floor lower in the third, then it's more effective at shielding. Does that make sense?
Yeah.
And so it's because it's n equals 3, we drop down a level. That's why. Even though it's in the same shell. So this is why I had to write shell, because it's not so strictly defined. All right, so this goes back to our graph that we saw earlier. So let's go back to that graph here and take a look at this. Oops, past it. Do you see what's happening here? Add a proton, add a same shell electron. Z effective goes up. Add a proton, add a same shell electron. Z effective goes up. Add a proton, add a same shell electron. Add a proton, add a same shell electron. Add a proton, add a inner shell, a 3D electron. Add a proton, add a 3D. And so do you see how it flattens here? This is the transition block, the transition metal. And then the trend resumes. Add a proton, add a same shell. This is going into the 4p. This pattern's repeated over here, and it's also repeated over here for the lanthanides and the actinides. There's something called the lanthanide contraction, which is add a proton, add a inner shell electron. You know, because this is going to be the 4f when we're looking at the 5.
So are you saying each time you add a proton, Z effective should go up by 1?
Yes.
Since you're also adding a inner shell electron, it cancels out.
Right, it cancels out the effectiveness.
So Z effective stays the same.
Stays the same. Exactly, that's what I'm saying. All right, let's take a look at this shielding and penetration in a little bit more detail here. Do you guys recognize these graphs? What are those?
Radio probability distribution.
Yeah, the RPDs. And it's hard to see here, but when you look at the 1s are inner shell electrons. Are they effective shielders? Yeah, they're effective shielders because if you have the electron density here, this is expanded. If you have this purple electron density here blocking off the nuclear charge, then it's going to effectively shield the blue and the green. And the black. The black you can barely see here. And so this is inner shell electrons are effective shielders. Whereas, how about same shell? Let's look at the blue. Do you think the blue is going to be really effective at shielding the green?
No.
No, same shell electrons, not very effective. Inner shell, effective. But how about this? This is now inner shell. The blue and the green are inner shell. The black would be outer shell now. You can see inner shell electrons, effective. But if we threw in another black electron, no, not very effective at shielding. And so with the RD, what is it called? RPDs, we can see the shielding effect more clearly with the 1s, the 2p, 2s. We can actually do a calculation to figure out what Z effective is. These are what we call semi-quantitative or calculations in which some of the numbers are estimated. And so there's something called Slater's law or Slater's rule that we use to do that. Z effective is going to be the nuclear charge minus the shielding. In the book, there's a homework problem about how to estimate the shielding. And the shielding is a very simple formula. Is it a same shell or inner shell? And it's actually a little bit more complicated than that because it depends on how inner the inner shell is. But you can look at that. I'm going to go through it. And so here you can see an example of the calculation. 12 minus 8.5 minus 1/3 gives us a Z effective of plus 3.2, something like that. We aren't going to really do any of these calculations. Here, this is an example of same shell shielding. How much does this electron shield this electron? Not much. Same shell. Actually, but how much does the core, how much do the gray electrons, so they don't show it, but how much do the gray electrons shield these? A lot. All right. Well, this is something we should be able to calculate, right? Those are semi-quantitative, estimates. But why not just, we know the theory. What's the theory? Quantum mechanics. So why don't we just do a quantum mechanical calculation and forego these semi-qualitative guesstimates about what the shielding is, right? Because all that stuff was pretty much. And so what do we use to do it? We use the, this might be hard to read, but this is Schrodinger equation, right? Because you use the Schrodinger equation. That comes from quantum mechanics. Let's do the calculation. But there's a problem. The Schrodinger equation can only be solved exactly for the hydrogen atom. It's pretty much, it's impossible to solve for anything more complicated than the hydrogen atom. Well, if it's impossible to solve, do you just give up? No. We don't give up, otherwise you can't make any progress. So what we do is we make approximations, and not only do we make approximations, but the math, even with the approximations, becomes quite complicated, quite difficult to solve. So we use an iterative approach. You know what an iterative approach is? Over and over again, like, you've done one. Like, what was it? Something you had to do over and over again. I decided not to put one of these on the last test because I didn't want to stay there too late.
Hess's law.
Not Hess's law.
Successive.
Successive approximations. Successive approximations is an iterative approach. And hopefully that iterative approach converges on your answer, right? Sometimes it doesn't converge. You trash that calculation, start over again, set up things, the parameters a little bit different. This is what I did when I was a student at UCLA. You start the computer calculating. You come back the next day and cross your fingers that it converged onto an answer, right? And so one of the reasons I didn't give this successive approximations is because I've seen people work on the trying to get it to converge, trying to get that answer, and they're at 50, 60. I had one person there for a very long time, many hours, and I should have checked to see what they were doing, but they were just doing one successive approximation guess after another. And so when I looked at their paper, they had about 50 or 60 numbers that they guessed, and they still didn't get the answer. And so it's just one of those things. Well, the same thing happens in quantum mechanics. You do these iterative things where, well, we have computers to do it. But even with computers, it can take a long time if it doesn't converge. And so this iterative approach, called the self-consistent field method, SCF. SCF was devised by Hartree in 1936. SCF is still used today with computers. And so we do SCF calculation here. Okay. There are others as well. But the calculations aren't so easy, and so this is why we still rely heavily on factual data. Otherwise, we should be able to calculate everything, the radius of the atom, everything else. But the radii are determined not from theory, the radii are determined from experiment. All right, what else is determined from experiment that we should be able to calculate? Well, the ionic radius. And so let's take a look at the ionic radii. And did I talk about ionic radii at all? No? Okay. So let's talk about sodium. For example, when sodium loses an electron, what happens to the side? It gives about 1/2. When magnesium loses 2 electrons, what happens to the side? It's a little more than a half. Not quite a third. A little, actually not a little more than, the size gets cut down by a little more than half. But the size of the ion is a little less than half the original size. And so in other words, when we lose that electron, then we have a lot of protons and fewer electrons. The imbalance in proton-electron ratio allows electrons to be pulled in much, much closer. And so here's the general rule of thumb. cations are smaller than the atoms from which they are formed. Well, we can go beyond that, because once we look at the data, we'll see that cations are about, what? Half the size. So let's take a look at the data. And let's see if that holds true roughly. Let's pick one. Calcium, 197. Calcium 2 plus, 100, about half. You look at all the blues are about half the size, no matter their charge. Let's look at iron 3. Iron, 124. Iron 3, 65. That's about half the size, even though it lost 3 electrons. And so regardless of the charge, cations are about half the size of the anions, and the cations in blue here. Okay, let's do the same thing for the anions. And take a look at the anions, and what would you say, just based on your observations? Anions are about double the size, exactly. Anions are about twice as big, cations are half as big. And that holds true. Look at the charge. Nitrogen 2, what's this anion called? Nitrite, about double. Even though it gained 3 electrons, a little more than double. Oxygen 2 oxide, it double. Fluorine 2 fluoride, about double. So just roughly a double. And this creates kind of a weird trend here. The weird thing about this is now the table is kind of flipped. Before, the biggest atoms were on the left. Now the biggest atoms are on the right. And so ions, the biggest are on the right, smaller on the left. And then it gets smaller. Like the biggest atom, neutral atom, is bottom left. The biggest ion is bottom right. The smallest ion is top left, sort of. Actually, helium plus, hydrogen plus there. Whereas the smallest atom is top right. And so just some trends you should be aware of. The next observation is this. If you look at all the green ones look bigger than the blue ones. And so let's pick the biggest blue one, rubidium plus, 149. Let's pick the smallest green, fluoride, 133. And you see, with just a few exceptions, cations are smaller than anions. Cations are smaller than anions. How much smaller? A lot smaller. So cations are a lot smaller than anions. So those are some general trends that you want to be aware of for size. Did we talk about the electron configuration? For example, iron plus 2. Did we talk about why iron plus 2? Does that make sense? We did. Iron metal is argon, 4s2, 3d. 3d6. Iron metal is argon, 4s2, 3d6. Iron 2 has electron configuration. Which one do we lose first? The 4s electrons or the 3d? The 4s. And so iron 2 would be 3d6. Iron 3 would be 3d5. 3d5 is kind of special because 3d5 has a half filled D. But I don't know how significant that is because cobalt 3 plus would be d6, 3d6. And so maybe that's not so significant. But it's just an interesting connection there. All right, let's continue on here with ionization energies. Next. Ionization energy is the amount of energy it takes to strip an electron off the gaseous atom to form a gaseous ion. And we do this one electron at a time. So magnesium likes to form Mg2+. Well, when we do this, we'll first have to form Mg+. And that is, because you can't kill two birds with one stone. So if we shot a photon of light at magnesium, this photon of light would have to have 738 kilojoules per mole of photons worth of energy. Is violet light enough, do you think? Violet is 390 nanometers, the highest energy. Is that enough? No. Because violet light at 390 nanometers only has about 307 kilojoules per mole. Is that what you guys calculated? Approximately, yeah. And so we need what? What kind of light would you need?
UV.
Probably UV, right? So we shoot a UV photon, knocks one electron off, and then we start off with Mg+. We'd have to shoot another photon here, but would it be the same energy? No, it'd have to be higher energy, because each successive ionization is going to cost you more energy, because the number of protons, the number of positive charge, the amount of positive charge stays the same, but the electrons become fewer, right? And so you have more positive charge pulling in fewer electrons, essentially. And so, so it's going to be harder. You can see that this is probably still going to be UV, maybe not X-ray. X-ray's got to be orders of magnitude bigger. That's just twofold. So let's take a look at some ionization energies here. Oops. I better shrink this down so you can see. Okay. So let's take a look at I1, first ionization energy for sodium. So we knock one electron off sodium, it costs us about 500 kilojoules per mole. 500 kilojoules per mole, is that visible light? 500 kilojoules per mole. No, it's probably going to take more, a little more than that. This is for the gaseous atom. This is for the gaseous atom. This is not necessarily for the metal. The metal is going to have a slightly different ionization energy, because it's not a single atom, but it's in a crystal of metal. But nonetheless, it's 500 kilojoules per mole. Does 500 kilojoules per mole sound like a lot of energy, or not that much energy? It turns out that's not that much energy, because we know that sodium is a powerful, not oxidizing, sodium is a powerful reducer, meaning it gives up its electrons easily. But the thing is, does it give it freely? No. It's just that the energy cost is kind of small. So even an extremely weak oxidizer like water has enough to strip. And so water has enough. All these oxidizers are going to have fairly low ionization energy, so 500. But take a look. Is water going to be strong enough to strip the second electron off sodium? No. If you look at it, the ionization energy went up by about 10-fold. Why? Okay, number one reason is, the electron used to be in 3s. Now you're trying to ionize a 2p electron. And 2, it's a filled core. And so, in other words, you're trying to ionize a core electron here versus a valence electron. And a core electron is going to cost you dearly. Look at magnesium. 737, 738 for the first, 1451 for the second. The third, a lot more, almost 8,000. Why? It's a core. And so the valence electrons cost a lot less energy to ionize than the core electron. And so aluminum 3+ is common. First, second, third, and then quite a bit of energy here. As we go along, take a look though. Here, phosphorus. First, second, third, fourth, fifth. To remove the fifth valence electron is going to cost you 6,000. Is that a lot of energy? Yes. I mean, 6,000, that's way more than sodium. Taking a core electron off sodium. And yet that's still a valence electron. And the reason is, yes, it does cost you dearly, but do you ever see the P5 plus ion?
No.
You know why?
It's hard to
It's going to cost you way too much energy, right? Way too much energy. But you've seen this. Phosphate has phosphorus in the +5 oxidation state. And so what's the difference between a +5 oxidation state, that is phosphorus lost 5 electrons, all its valence electrons, versus P +5?
The amount of energy spent.
Yeah, the amount of energy. Even though this is called a +5 oxidation state, the true charge on phosphorus is not a full +5. It's not a full +5 because the oxides here, the oxygens around this, can donate a little bit of electron density back. And so it's because of these oxygens around here, this is how it stabilizes the +5 oxidation state on phosphorus. But if the +5 is not totally accurate, that is, if oxygen gives back some of its electron density, then why don't we do quantum mechanical calculation to figure out what the true charge on phosphorus is? What is the true positive charge on this? We can do that. That's not too difficult, and you get a number for that, right? But the situation is, do you want to do a complex? No, you don't. You want to keep it simple. And so this is what we do. You know, we were talking about the 0 points. You know how many different 0 points we got, like in that thermal table? We have the same thing here. So for example, a +5 on phosphorus, does that mean the same thing as a +5 on chlorine? No, totally different, doesn't it? It's totally different because those are from two different reference points with two different species entirely. And so these numbers are just tools to help us understand. So the thing is, if we compare phosphorus with other phosphorus species, then these numbers work quite well. You know, a +5 on this phosphorus versus a +3 on another phosphorus, we can totally tell the difference. Like here, PCl3 is a +3. These two phosphoruses are going to behave quite a bit differently, right? And so we can make comparisons like this with an arbitrary 0 point. You know, this is a totally arbitrary scale. But for us, it's okay because this is a fair comparison. We're comparing things that are alike. But a lot of people ask me this, well, what about ClO4 minus, you know, with chlorine in the +7? Or what about ClO3 minus, you know, with chlorine in the +5? You know, okay, oh, I got chlorine in the +5 here, phosphorus in the +5, they must be the same. No, not at all, because these are on different scales. You know, this is like trying to compare Fahrenheit with Celsius or trying to compare apples with oranges. It just doesn't work, and this is why things are complicated. Things are complicated because you have to keep track of all this stuff, right? Because if it were easy, then you know, a computer can do it, or some kind of machine can do this, you know, and make these predictions. But since this is much more complex, then you know, not everybody can do this because not everybody is going to really understand, you know, that the numbers aren't absolute like that. And these aren't like Kelvin temperatures where, you know, +7 here and +5 here is absolute in that sense. Well, anyway, going back to this, we can lose all, you know, on sulfur we can lose up to 6, but you know, that's going to be hard to stabilize. But to go sulfur +7, what do you think? No, that's crazy because that would be core. So typically the core electrons are going to be quite unreactive in chemistry because it just costs too much energy. And chemistry happens with this, the valence electrons here.
So, like, since they're so small, then how do they hold so much strength together?
Since they're so small, what are so small?
Like the protons and the electrons, like why does it take so much when they're so tiny to pull them off?
If you think about it, it is so small, but do you know that if you had one stick of dynamite versus just taking like one uranium atom, actually, we can do some calculations. It's so small, but the energies that we're dealing with are quite significant. Are you saying, You're saying about the electrical or about electrical forces?
I mean, because we're talking about plucking them off.
Oh, plucking
It's
off.
harder and harder,
Okay.
but I was just trying to figure out why is it so hard if they're so small, you know? It's like
Oh, it's because it's becoming more and more concentrated, and more concentrated the smaller it gets, and so all that charge is getting, at least the positive charge is getting more concentrated relative to the negative charge, that it becomes harder to pluck off. That's the reason. Something like that. I'll try to think of another analogy, but maybe Sherry has something.